And where go?
So, let's pick up from where we left off last time. So last time you spoke about interval notation. It's kind of where we left it off. Let me just redo that table to remind you guys. So we had a way to look at things, which we called inequalities. And they have a corresponding interpretation, or a way to write them down, which we call interval notation. And you should also know how to graph them. So, what were the ones we looked at last time? We looked at x greater than a, x greater than or equal to a, x less than a, x less than or equal to a. Looked at x is strictly between a and b. X is between a and b, potentially equal to b. X is between a and b, potentially equal to a. X is between a and b, potentially equal to either of them. So and remember how we did this one? So that means open parentheses to infinity. That's the interval notation for this idea. This is, you use brackets when you can include the number, you can be equal to the number. Use open brackets when you cannot be equal to the number, or parentheses as we call them. So these would all look like this in interval notation. So your a and b are real numbers. Now, the pictures for this would look something like, so let's say this is a number line like here. These are number lines. So someone tell me how these pictures would look once I kind of get set up here. Like if we were to sketch it. So what would the top one look like? So let's say I pick A to be at this point. This is A. Yeah?
The arrow goes to the right forever.
Yeah, what about at 8?
Sorry? Oh, you put an open circle at that
Okay,
point.
so there's an open circle here, and the arrow goes like that. That would be someone sketching this. When you can be equal to, you put a closed circle. And it goes like that. Of course, less than is similar, but you go the other way. Less than or equal to is similar. You shade it. You go the other way. Between A and B, so here are A and B. So once you cannot be equal to, you have open circles. But once you can be equal to something, you put a closed circle. And then you fill in draw a line that covers all the real numbers that would make this thing work. So this here is shaded, that is unshaded, and for here, both of them are shaded. Now, last time we also spoke about set notation for or and. You guys remember what or looked like? Yeah? Just the U, and was that. So it means when you want to combine two such statements. So someone could say something like, x is between 1 and 3, not including 3, or x is greater than 7. So in interval notation, you would write this as 1, 3, not equal to the or, you write as a u, and greater than 7, actually that. So you can combine statements with the or and the and. And of course, if you wanted to sketch this, you write down the numbers 1, 3, 7. Here you'd be shaded. Here you'd be an open circle. And over here you'd be an open circle. And into the arrow. So these are the interval notations. And being able to sketch them is going to be pretty convenient. And I think I'll show you an example right away where it's going to be convenient. Right. So let's look at some examples where sketching them might be convenient. Now, this is an example that would include an idea that we haven't spoken about yet, but I'm confident that you've seen it before, so let's kind of be brave and go ahead. But we will come back to it. It's the idea of domains. So here are two problems. I want you to find the domain of the following functions. Y equals the square root. And here, y equals the square root of 1 minus x divided by the square root of 9 minus x squared. Okay, so someone remind me of the idea of domains. What do you remember about domains? What is a domain? Huh? The x values that do what? Someone asking for a domain. What are they asking you for?
All possible values of x.
Right. Possible values in the sense that all the numbers that I can plug into this expression and it will make some mathematical sense to talk about it, right? So it's the set of all input values for which the function is defined or for which the function actually works. So if the x's aren't given, if you aren't given a restriction, you always assume just like take up the largest set possible for which this is going to work. So without any more information, I just want to now know what are all possible x values that I can plug into this thing that will make it work. Notice that here there's a square root. Now that automatically comes with some restrictions, right? So recall for the square root of some function to be defined, what is the restriction on the function? Tell me what that function has to be like. It can't be negative. So the function itself must be greater than or equal to 0. Right? So there's an inequality restriction here. And this works for square roots. It also works for any even number. So this will only work when your function is positive. And of course your function has to make sense otherwise. Right? So for A, we need that 4 minus x squared must be greater than or equal to 0. Now, does anyone remember how to actually solve the inequality? How would you actually solve that? How do you know when 4 minus x squared is greater than or equal to 0? Yeah?
Solve for it, like you would solve it if it had an equal sign.
Right, so you pretend that it's an equal sign for a little while. So pretend that this was 4 minus x squared equals 0. How would you actually solve it if that were the case? In general, you want to solve a polynomial equation. If it's not linear, you want to factor. First thing you do is factor both sides. What is going to be the factors of that? Huh?
2 minus x is equal to
2 minus x and 2 plus x. Now what do? Set each equal to 0. So from here you get x equals 2. Here you get x equals minus 2. But now you remember it's not an equation, it's an inequality. How do you determine which values work knowing it's an inequality? You plug in numbers, right? Now the nice thing here is I would actually draw a picture. I would have a minus 2 here, I would have a positive 2 here. Knowing that I can be equal means that I'm going to have circles that are shaded here. Because equality is possible. And now all I have to do is just plug in numbers in between these to see which ones will actually work, right? So I can pick a number, pick a random number, let's pick 0. I can pick a random number over here, let's pick 3. Just pick some nice numbers that you can calculate easy, right? So don't be like pi squared over radical 2, no, like pick 3, it's a nice number. Minus 3 would be a nice number over here. And what you're going to do is you're going to plug into the original expression and see if it actually makes sense. So I would plug a 3 into here, I would get 4 minus 9. 4 minus 9 is negative, which is not greater than or equal to 0, which means over here it doesn't work. If I plug in 0 into here, this means 4 minus 0, which is greater than or equal to 0, so over here it does work. Plug in a negative 3, I would again get 4 minus 9. That gives me a negative number, so that does not work, which means that the answer is between these two. Now, on the table I wrote before, that shows you how you can write the domain in interval notation. So in this case, the domain would be, let's move it over here. You would put minus 2, comma, positive 2. Right? And that would be your answer. Right? It's all things between minus 2 and 2, including either minus 2 or 2. These would be all the numbers that's solid. Now, yeah.
Couldn't you just plug in those x values into the equation and get it from that way instead of drawing that whole entire diagram?
Plug in which x values?
Like, no, I mean the domains that you got from the 2 minus x, like you get, say, for example, you get that 2, and you plug it into the equation that you got right there.
It'll give me 0. If I plug in 2 here, I get 0.
Yeah, exactly. So like, oh, okay.
Right? But I want to know when am I bigger, right? So getting exactly 0 isn't going to help me very much. I want to know when am I bigger. Or, now, let's just do a little tweak on this one, just so you can see some sort of variety here. I could have asked you the same thing, but different. Where if I instead asked you x squared minus 4, you'd start out the same way. You know, I need x squared minus 4 to be greater than or equal to 0. This would mean that x minus 2, x plus 2 is greater than or equal to 0. This means I'm going to test x equals 2 and x equals minus 2. Initially, I would have something looking very similar. Equality can happen here, so I would shade those. But now when I plug in numbers like minus 3, 0, and 3, if I plug in a 3 here, I would get 9 minus 4. That actually would work. If I plug in a minus 3, that would work, and then this wouldn't work, and then over here would be the answer for that one. And then you would actually write the domain is minus infinity to minus 2 inclusive, or give me 2 to infinity. So just by someone flipping the sign, it can really change what the answer is going to look like. But at the end of the day, to make sure you know where your answer is, drawing the picture is going to be a nice way to actually tell you where the answer should be. Yeah?
When would you use and with that symbol? Like if we were to give an example.
I can't think of a question like this where and would be the answer, actually. It's going to be one or the other. if there's anything that you would use and, they'd be overlapping in such a way that you kind of not have to mention it. There's going to be a kind of and situation when dealing with something like this, and you're going to realize that you're still not going to need to use the and symbol at any given time. Right? So with domains, I can't really think of an example I would ask you where an and would be appropriate. But so far, these two examples, do you get what we're doing? Okay. Now let's look at this example, which is slightly more complicated. So the second example shows you that sometimes you have to keep your eye on several things at a time. So if I'm looking at this guy, oh, let me show you something else with this. Here's another way to actually do this without any calculations. And you can sometimes do this when it's simpler like this. Here's another way, part A. Is to look at the actual graph. Right? Now a lot of times the things that I'd be asking you, you'd be able to graph those pretty easily. Now if you look at y equals the square root of 4 minus x squared, and you know that we need 4 minus x squared to be greater than or equal to 0, one thing you might ask yourself is, what does y equals 4 minus x squared look like? Right? Now, hopefully, at this point you know that that would look like that, right? Where it goes up to 4, it'll cut here at minus 2, it'll cut here at 2, right? And now you can tell in the picture, from the picture of the graph, exactly what you want. Where is the picture greater than or equal to 0? It's just wherever the graph is above the horizontal. So notice that the graph is above the horizontal. We're above horizontal for x in minus 2 to 2. So you can just look and know that the middle part is going to be your answer. Compare that to if we had y equals the square root of x squared minus 4, and you know you need x squared minus 4 to be greater than or equal to 0, then you look at what the picture of that looks like, which hopefully you know that's what it looks like. That's going to be minus 4, that's going to be 2, that's going to be minus 2. And now you're going to look at where is this guy greater than or equal to 0, which means where is it above the horizontal? Well, clearly it's above the horizontal over here, and it's above the horizontal over here. Over here is when you're 2 or bigger, and over here is when you're minus 2 or less. And then you can take either this branch or that branch, and that again leads you to x must live in this. Questions on that idea? So sometimes you can use the picture. If you don't know what the picture looks like, you can again just factor it like you were solving an equation and just plug in values in between the numbers. So you have a couple ways to actually look at this. Let's look at the other one. We'll again see a nice way to use our intervals here to help us. Okay, so someone tells me what I need here. What needs to happen for this to work? Yeah, go.
1 minus x needs to be greater than or less than 0.
Greater than or less than 0? Needs to be what? What do you mean greater than or less than 0? Yeah.
Greater than or equal to 0.
Greater than or equal to 0, right? That's where the radical is going to work. Is there any other restrictions on this function? Yeah?
The denominator cannot be 0.
So we need 9 minus x squared to not be 0. Any other restrictions? Yeah? Huh?
X can't be equal to 3.
That's exactly the same as saying this, right? So if x is 3, this would be 0, and so that, yeah. So this automatically tells you x cannot be 3 or negative 3. Any other restrictions?
that one also has to be greater than or equal to 0?
Right. There's a radical here, which means it has to obey the radical rule. So you also need 9 minus x squared to be greater than or equal to 0, but you know you're going to ignore the equal part because of this restriction. So this has three things going on with it, right? There's a radical in the top, a radical in the bottom. Each radical has their requirements, and then knowing that it's a fraction and knowing that you can't divide by 0, because Jhevon told you in lecture 0, you can't divide by 0, this becomes a requirement. So now there are three things you have to keep your eye on. And how do you actually go about doing that? Well, you do them one at a time, and then you draw the picture in interval notation, draw all pictures on one graph. So here's how, so another way you can look at this, which kind of leads into your last question, is you need this and that to work, right? All of them needs to work. Because if any one doesn't work, then the entire function doesn't work, right? If this didn't work, we divide by 0. It makes no sense. If this doesn't work, the top doesn't work, so that's not even a real number. If this doesn't work, the bottom won't work, so that's not a real number. We need all of these at the same time to work. Now, what does that mean we need to happen? So what you would do is you would do them one at a time, as I was saying. So we first deal with 1 minus x greater than or equal to 0. What does that mean? I need. Tell me about x. What does x have to do? Huh? Add x to both sides, and then you get
1 greater than or equal to 10.
right. Now we know how to write that in interval notation, right? That just means x. This, if you write, so this means 1 is greater than or equal x. Now there are a couple ways you can think about it. You can also think of it as x is less than or equal to 1, right? So this means your x is somewhere over here, right? If you turn it around. This is the same, this is equivalent to saying x is less than or equal to 1. Just turn it around and keep the Pac-Man mouth aimed at the 1, right? So Pac-Man, he always goes after the bigger guy, right? So saying 1 is bigger than x is saying the same as x is less than 1. So that's equivalent, which means we're 1 or something less. Now, what would it mean to say that 9 minus x squared is greater than or equal to 0? How do I solve that? Factor, right? Same as last time. What are the numbers we get here?
X is 3, x is negative
3 or negative 3. And of course, we know that if we automatically get that if 9 minus x squared is equal to 0, that means we cannot be equal to 0, it means we can't be the 3, and we can't be the negative 3. So we have these three competing ideas, right? Now how do we actually figure out which set or which set of numbers actually gives us the answer? Well, again, you start sketching. You sketch one at a time. So I would look at the first one, and the number 1 comes into play, and so I'm going to sketch that. To be less than or equal to 1 means I can be a shaded circle. And going back, and that's this requirement here. And then I can do so now the other one, I have to do a little bit of testing here. Now one thing you can notice is that this is an upside down parabola. So the middle is the part that you're going to want. But again, let's say you didn't see that right away. So the minus 3 would be over here, the 3 would be over here. Now I know I cannot be equal to them. So there has to be an open circle at this point. So I'll draw them on another level, open circle at that point. And that's me taking care of this. I get to use multiple colors on this. This is awesome. Okay, maybe I'll go with blue. Although they say if you're colorblind, blue and green, hopefully no one's watching this. So So this is blue over here. Now what would that mean? Well, what I would do is I would plug in a random number, say -4. Plug in a random number over here, say 4. Plug in a random number in the middle, say 0. So I'm only focused on the 3 and -3 now, so ignore the 1. I've already taken care of the situation with the 1. So if I plug -4 into this, I get 9 minus 16, which is negative, which doesn't work. So this does not work. If I plug in 0 here, I get 9 minus 0, so the middle one works. If I plug in +4 here, I get 9 minus 16, so this one doesn't work. Which means for the 3, strictly in between these works, right? Right? Now here is how you would interpret AND. AND just means overlap. They all have to be true at the same time. So if you look over here, there's only one of them that's true, right? And if you look over here, there's only one of them that's true. We need all of them to be true at the same time. So what we're doing is we're actually looking at the overlap. So notice that the overlap happens here. So now I'm going to talk about what set includes all of this at the same time. And what do you think? What's the overlap? -3 to 1. Parentheses or brackets? -3. Right. At 3 it's open. Parentheses. What about at 1? Closed. So that's the domain for this one. Putting a lot of ideas together here, right? But being able to draw them certainly does help, right? So you have all these things written down, you're like, what does this all mean? How do I put it all together? Drawing a picture is a nice way to put it together, right? When you have several things having to be true at the same time, what it means is you're drawing a picture, you're looking for overlap. So you still don't need that AND symbol. And if there were several positions of overlap, you'd still use the OR here, but that's kind of the idea. So that's how sketching can be useful. And figuring out domains of functions, that's going to be very important. It's going to be important in calculus because if our functions don't work, you can't do calculus on them, and all sorts of situations. You're going to need to be able to talk about the domains of functions all the time. And in this class, I'm going to be specifically asking you questions of the form, hey, find the domain of this, find the domain of that, find the domain of that. And you'll put that into practice or into use in future classes. So, any questions on that? So, let's move on. Let's talk about another idea. Again, one that I would have expected you've seen already, but let's make sure that we remind ourselves of what it is. It is the idea of an absolute value. So the notation, you might recall, is straight line bars. So this means the absolute value of x. Anyone knows how it's defined? If someone says, what's the absolute value of x? What would you say? Yes?
The number of units x is away from 0.
Okay, give me a mathematical way. Express that in symbols. That is correct. If you had to respond in English, you can say on the number line, this is the number of units x is away from 0. That's fine. That's the distances portion. What's the mathematical, if you were to write down a formula for it? So that's the definition that less people know, and that's the one that's more important for calculus actually. So let's actually go about that. Here's how you define it mathematically. The absolute value of x is what we call a piecewise function. It comes into pieces. It behaves differently depending on where you are. Now, what do we know about the absolute value of a positive number? Like I say, absolute value of 3, what happens? It's still 3, it just stays at 3. Which means, what is the absolute value of x? Well, it's x in the case that x is greater than 0. What if I put in a negative number, like absolute value of negative 3? It becomes positive 3. In other words, what you can think of it as, positive 3 is negative of negative 3. So what the absolute value does is it takes the negative of the number if the number is less than 0, and that way it turns it into a positive. Now by definition, we say it is 0 when x equals 0. So this is a function that is defined in pieces. Now, from this we can get to a graph. The graph of the absolute value. This was something that I asked you on the diagnostic, I believe. I think I did. So how you would graph this is, again, you graph it in sections. This is how you graph piecewise functions. So you look for when x is greater than 0, that's over here. And what are you going to graph? The graph y equals x. Now remember what y equals x looks like? Hopefully you do. It's just a straight line going like that. So for over here, you have this graph. Just a straight line going up that way. When your x is 0, you have 0. So this gets shaded in. And then, so over here, it's y equals x. Right here, it's y equals 0. And then over here, it's going to be y equals minus x, which looks like a graph, a straight line going like that. So that's the picture. You get a V, right? It's supposed to be symmetric. It's roughly like 45 degrees on either side. So that's the picture, right? And you can plug in, so like I was saying, if you plug in 3, you would get the value 3. If I plug in minus 3, you'd also get the value 3. It's going to be symmetric. So whether you plug in a positive or a negative number, the absolute value gives you the positive version of the number because it's actually describing a distance. So it looks like a V. So that's the absolute value function. So knowing it as a distance is useful a lot of the times, but most of the times, this definition is going to be very, very useful. And we'll see that especially in calculus, knowing this definition of absolute value is useful. But even in this class, I'll show you some examples where thinking of it this way is going to help you solve the problem. When thinking of it as a distance is just going to confuse you. So you should know the definition, you should know the graph. These are very important ideas. Do I have any examples here? So let's talk about the properties of the absolute value. Now normally when I mention properties of something, I'm talking about the algebraic properties, which means how you do arithmetic with the idea. So, one, you should know that for any real number A1, the absolute value of A will give you a number greater than or equal to 0. 2, if you have the absolute value of A, it will give you the same output as the absolute value of negative A. 3. Absolute values distribute across products. So if I have the absolute value of a multiplication, I can think of it as the multiplication of the absolute values. That'll actually work. Or it also distributes across division. So if I have an absolute value across a division, it's also the division of the absolute values. 5. This one is also important. Less important in pre-calc, more important above pre-calc. But it even has a name. It's that important that we name this one specially. It's called the Triangle Inequality. So this is basically that saying if we're adding things in an absolute value, it's actually not the same as adding the absolute values. It is going to be less than or equal to the sum of the absolute values. So it's very important that you realize you can distribute an absolute value across multiplication and division. It does not distribute across addition. If you split up the absolute values, you can actually get something that's larger than the original number. I can give you an example so you can see that that's actually true. Let's say I have A equals 1 and B equals -3. Then, if I have A plus B in absolute values, this is just 1 plus -3. That's going to give you -2, which you know is 2. Whereas if I give you absolute value of A plus absolute value of B, that's going to be absolute value of 1 plus the absolute value of -3. We know the absolute value of 1 is just 1, absolute value of -3 is just 3, and I get 4. Notice that this is bigger. Right? So the absolute value does not distribute across sums. If you split an absolute value across pluses, the split version is potentially larger than the original version. It's very important for you to know that. It's called the triangle inequality because there's a picture that goes with it that is like triangle. Looks like a triangle. And I'm just going to do it. If you don't get it, don't worry about it. You won't have to think about it. But it's more like when you're thinking of vectors and you're drawing arrows all over the place. So if you have an arrow where the size of that arrow is A and you have another arrow where the size of that arrow is B, and you think of them as vectors, it turns out that the vector A plus B is going to be the vector that moves in the middle. That's also going to be important for physics. So this is going to be the vector A plus B. Now, vectors, you can move this one to that side, so notice that I can move the B over here, that's also going to be B. And now you just take the idea that's correct. Shortest distance between 2 points is a straight line. Which means if I wanted the shortest distance between this point and that point, this is the shortest distance. Now, notice that another way to get from this point to that point is to move here to this point and then to that point. This has to be longer than that. Which means if you take this distance plus that distance, you get something bigger than that distance. Triangle inequality, right? Because there's like a whole triangle being imagined. That's more important for after this class. If you got it, great. You need to get that by the time you take general physics, though. That's going to be, dealing with vectors is going to be important. How we can think of distances. I think that's the next thing I want to mention. Means now distances, if A and B are real numbers, remember that was the symbol for real numbers, this is the symbol that means these guys belong to this set. We define, some weird D, the distance between A and B by, here's the notation we usually use for it. DIST parentheses A comma B. This is the distance between A and B. And we defined it in terms of the absolute value of the difference of the numbers. So for example, I can ask you, what is the distance between -2 and 5 on the number line? Now intuitively we know that the answer is 7. Right, you can actually draw a picture here. That's -2, that's 5. And if you count the number of units to get from this point to that point, you'll count 7. Computationally, you can also do this as the absolute value of 5 minus the 2. negative 2. You'll clearly see that this is the absolute value of 5 plus 2, which gives you the absolute value of 7, which is 7. Right? So you can actually calculate that. So you can throw the absolute values to make sure you actually get the right number. Distances are always taken to be positive in general. But to generalize this idea, in 2D. Once you go to 3D, all bets are off. Kinda. But yeah, for those of you who are going to be in sciences and you're going to be taking Calc 2, you're going to be doing things like volumes of revolution, and there's going to come a point where they're going to tell you, oh, you have to subtract this from that, and your professor might explain it in a complicated way, but the idea is exactly what I'm going to tell you now. It's very simple. So, 2 semesters from now, when you're doing that topic, oh, Jhevon told me about that. It's like, yeah, I remember that. It's just, this is all it is, right? And this just means horizontal distance is the following. If you're measuring a horizontal distance, what you want to think of it is right minus left. If you're measuring a vertical distance, you think top minus bottom. There are a bunch of places in Calc 2 and Calc 3 where just that idea alone is going to make one problem go from confusing to that's actually trivially easy. You get to Calc 3, you're drawing things in 3D and you're like, I don't understand what's going on. Figure out who's on top and who's on bottom and everything sets itself out. Or figure out who's on the right, who's on the left, and everything will set itself out. And you'll know which functions to put in which positions and how to do the calculations by this idea. It's a very simple but important idea. Right? So if I gave you, find the distance between minus 2 and 5. Who's on the right? Well, 5 is. Who's on the left? Minus 2. The distance is right minus left, 7. Where are we? And we're building things from the ground up, so I'm still talking about. And it's kind of weird because I am going over a lot of the things that you'd have seen in an algebra class back in high school, but I just want to make sure everyone's thinking about them the right way and in the easiest way possible. So I want to talk about Pemdas. So, I don't know, a month ago, a few weeks ago, it came up in my news feed and there were a bunch of YouTube videos made about it. Even made it on the news, apparently. But it's one of those math problems that stumps the internet, you know, and everyone was like arguing, people were breaking up their friendships over, what, you think the other, people getting divorces and all sorts of stuff. And the problem was, that was the problem, right?
Oh, I remember this.
You actually remember, right? Like it was like, oh my god, this stumps the internet, everyone's like, people are arguing. There were a bunch of people that thought the answer was 1, and then there were a bunch of people that thought the answer was 16. And there's like arguments about, oh, what is it? It's 1. And like, no, it's 16. You believe it's 16? I can't trust you anymore. And like, forget about it. Yeah, it was crazy. Now, there should be no argument about something like that. And really, when that happens, math people just roll their eyes. But yeah, this is just another example of when people just make something simple so complicated, and it just gives people the wrong view of mathematics. See, if you really remember Pemdas, there is no ambiguity at all. There should be no argument. What is the answer? Does anyone know?
It's 1. It's 1.
You think it's 1?
It's
There is
1.
1.
Does anyone think it's 16? Let's see, she's like break up with you, like, what? You think the answer is like, she was looking around, I want to know who thinks it's 16. Right? Okay, so here's where the disagreement comes from. So some people like, okay, you do what's in the parentheses first, everyone knows that, right? So, okay, that's a 4 over here. But then they're like, that 4 is attached to the 2. And so it's 2 times 4, that's 8. And then I take 8 divided by 8 and I get 1, so that should be 1. And then other people are going to like, well, yes, you start out by adding these two, so that gives you a 4. But you know what I would do? I would take the 8 divided by 2 first and get a 4, and then multiply by that 4, and I get 16. And people are arguing, let's put this to rest once and for all. Pemdas. Now, questions like these arise every now and then, and whenever they do, the misunderstanding is always going to happen where I'm going to tell you right now. Which I'm going to write in green. The green is where the misunderstanding is going to be. So, PEMDAS is a mnemonic, stands for parentheses. E stands for exponents. This means powers, like the little number that you would write up here. We're going to actually talk about that. M stands for multiplication. D stands for division. A stands for addition. And S stands for subtraction. Okay, so far so good. This is called the order of operations. That's what they refer to it as. Now, here's an important part. Just like what I mentioned last time with axioms, there is no real mathematical reason for this to be. It's just that everyone just decided this is the rules. If there's ever an ambiguity, this is the order we're going to do it in so that everyone gets the same answer and we all can communicate clearly. So this is a convention, right? There's nothing inherently better about multiplying than there is about subtracting, right? We just set up these rules so that everyone can be on the same page. So that's the first thing. Here's what people often forget. People often think that multiplication always supersedes division. This is not true. These two here, those pairs have the same priority. Right? Meaning, unless indicated by parentheses, you apply them left to right. You apply them in the way that they're read. Okay? Now, people forgetting that is what causes all the arguments. Okay, so, what is this actually? So, you follow the rule of Pemdas, which tells you work out what's in the parentheses first. So here, you would get 4. Here, there's a multiplication of 2. Here, there's a division of 8. Now, there are no parentheses anywhere that tells you what should be done first next, which means, according to PEMDAS, the two remaining operations are multiplication and division. These two have the same priority. If no indication is made, you read them left to right, which means this is applied first. You would get 4 here times a 4. The multiplication is applied second. The answer is 16. There is no argument on this. Every math person will tell you the answer is 16. Like, obviously, like, forget about it. This is the problem, right? This is going to come up with a larger thing where I'm trying to remember if it's going to be relevant in anything I'm telling you in pre-calc. It's definitely relevant in calculus. Students have this idea of memorizing pieces of rules. They never want to write down the whole thing. Like if I were to ask someone, what is the quadratic formula? They'll immediately tell you, oh, it's minus b plus or minus the square root of b squared minus 2ac all over 2a, right? Right? Minus 4ac all over 2a, right? That's not... The quadratic formula is an equation, right? No one ever remembers that there should be an x on that side. And at one point, it doesn't seem like a big deal to you. Like you tell yourself, if you remember this, oh, I know the quadratic formula. But you see, because you left off this little piece of information, doing things like that is going to come back to bite you later on, right? So there will come a time in calculus where you're going to be given a bunch of rules. And the tendency of a lot of students would be to memorize one side of the rule and leave off another part, the part that they think, oh, it's less important, or I know what's going on. And that's going to cause so much trouble. You don't believe how much trouble that's going to cause. So this is one of the principles here, not just to teach you PEMDAS, but this is a general principle that you're going to want to take. Whenever a mathematical rule is given to you, memorize it in its entirety. Every little jot and tittle and clause that goes along with that rule is important. And math people, when they're writing down rules, they write it down very specifically. And if you don't have one of the pieces of the rule, it's not a rule anymore. You don't assume it's true. Right? And I understand that it looks trivial right now, but it's like you forget these little pieces here and there, and it causes a lot of havoc in the future. And there are going to be times when here's one of the reasons why it causes havoc in the future. It's kind of like the same reason that people who know parentheses should be there, but they don't write it. And then later on they forget that there were these imaginary parentheses that they had. Right. Things like that happen. Now what happens when that happens, right? Why you would forget the parentheses, right? So when I was like, 5 minutes left, and you start freaking out, and then you just forgot the parentheses. You have to understand that your brain has two kinds of thinking, right? There are two sorts of thinking that your brain undergoes, right? There's type 1 and there's type 2, right? The type 1 is called fast twitch thinking, right? That's the one that if a saber-toothed tiger jumps out of the bushes, you don't think, you run, right? You don't calculate anything if a tiger jumps out of the bushes. Your brain just says, let's get out of here. You run without you don't even know what direction you're running in. You see, you just run in the opposite direction. No thinking happens, right? Then there's type 2. This is the deliberate or slow twitch thinking. And that's the kind of thinking where you kind of take your time and you deliberate and you figure out and then you construct things and you abstract things. Okay. Now, when anxiety takes over, you have to understand, your brain doesn't know the difference between a math test and a saber-toothed tiger, right? It just knows that your heart rate is elevated, that you start worrying about something, and so what it does is your brain actually switches to fast twitch thinking. And a lot of other hormones go off in your body that affects how it turns off your digestion, which is why you might feel queasy and palms are sweaty. It triggers a response in your sympathetic nervous system, right? This is science. You can look this up if you don't believe me. So what happens is, all that deliberate thing, like your invisible parentheses that you have to be on type 2 level to remember, once I go 5 minutes left and you start freaking out, that goes out the window, right? You're going to start forgetting little things here and there. And then your body goes into, your hands start trembling and all sorts of stuff because your body starts pumping out adrenaline because it's trying to get you ready to run from the tiger, right? It doesn't understand that you're on a math test. So what's going to happen is all that stuff, it goes away, and what you actually write down is what your brain is going to remember. It's going to say, oh, just do that and get out of here, right? Problems immediately. You get problems wrong that you shouldn't be getting wrong, and all sorts of bad things happen. We'll end there. Do we end now?
Yeah.
It's 45. I have like 3 more minutes. Where are you guys rushing off? Anyway, that's not enough time to do anything else. We'll stop there for now. I'll see you guys on Thursday. We'll talk about laws of exponents on Thursday and algebraic functions.